Hello everyone, welcome to Metsa Easy. Today I'm going to discuss about this resistor cube question, which is a very popular physics question. I haven't really seen it in an A-level paper, to be honest, but it's a very common thing in, for an example, physics challenge questions. I've seen this, and I mean, if you just Google the term resistor cube or something, you can see you get like multiple um, results. So it's a very popular one, and I think if you are an A-level physics student, it's definitely good to know how this one works. Now, I've already explained in a previous video about what the Wheatstone bridge is. Now, you need to have the knowledge of what a Wheatstone bridge is, or a balanced Wheatstone bridge, to understand how this one works. So if you haven't already watched that, I would suggest that do that one first before you come to this one. Now, you can just pause the video and try to do this question. So the idea of this question is you got 12 resistors connected in the shape of a cube, right? So 4 at the bottom, 4 at the top, and the 4 vertical ones. That's 12. And then, so the question is find the total resistance between A and C. Pause the video and see if you can figure this out. When you are ready to see my working out, you can press play. Alright, now for the convenience of referring to these things, I've just colored them. The bottom 4 resistors are colored in green, then the vertical ones are colored in purple, and the top 4 are colored in yellow. Now, let's say imagine practically making a resistor combination like this using actual resistors, some wires, right? Some metal wires. Now, what we are going to do is we are going to make this structure flat. So I'm going to imagine if I have this one in a kind of a stretchy sort of a metal, and I'm trying to pull out from these 4 corners in 4 different directions. So you can understand now. I can have my A like this, point A, and my point C like that. Now I have the 4 green resistors connected across. So we have point A here, point D here. Between those two I have a 10 ohm resistor. D to C, another 10 ohm resistor. Here also a 10 ohm resistor and another 10 ohm resistor. So I have 4 10 ohm resistors on the green, the 4 green lines. Now, starting from each like corner A, C, A, B, C, D, I have these purple ones connected like that. Now on each purple branch, I have a 10 ohm resistor. Here we have a 10 ohm resistor. Here we have a 10 ohm resistor. And here we have a 10 ohm resistor. Now you can see at the end of each purple branch, at the top end, they are connected using the yellow ones. And now here we can see the last 4 10 ohm resistors. So these are all 10 ohm resistors as well. So they are all identical to each other. So there you go. So now you can clearly see the green ones at the bottom, and then the purple ones that connect them, and then the yellow ones at the top. Now you can understand this as if you are looking this from above. Imagine you are looking at this thing. This is an eye, by the way. If you look from the top, like how you would see the yellow ones at the top. Then if you just pull the other ones, the green ones a bit out, and you can kind of fly it, right? Then it becomes a flat shape like this. Now you need to make it like that so that you can actually conveniently see what happens here. Now imagine you are connecting this to a power supply, to just any voltage across is fine. Now you connect it to a power supply which provides voltage V. Now the potential difference between A and C is V. So obviously the potential at point D is V over 2, because this is a symmetrical system. That's 10, that's 10. In this branch we have V over 2. Similarly, if you think about this branch here, this path here, going from A to C, but we go along the purple one, then this yellow path top, and like that and like that. Now in that branch, this one here is the midpoint, so that voltage should also be V over 2, right? Similarly, the voltage here is V over 2, considering the green path. Considering the other path, the potential here is V over 2. Now, this is really interesting. Now you get a balanced Wheatstone bridge situation. So, how does that work? Now, you can clearly see across this resistor at the top, there is no potential difference. Why? Because above it's V over 2, below it's V over 2. No potential difference. Same with this one. If you think about this one, there is no potential difference between it because it's V over 2 at the top, V over 2 at the bottom. Remember, according to V is equal to IR, if the potential difference is 0, right, obviously the current is 0, because the IR product should be 0, R will not be 0, but obviously for V to be, when V is 0, I is going to be 0. Right. So what that tells us is there will be no current through the 10 ohm resistors that are circled. Now, if there is no current, do you really need it? Because whether it's there or not, it's not going to make a difference. So that's the whole point that we discussed in the Wheatstone bridge one. So if you haven't watched it, please have a look. Now, that means I can easily remove it without having any impact on the rest of the circuit. So that one is gone and this one is gone. Now, why did I do that? Because there's no potential difference. So under any circumstances, there'll be no current through this. Right. Now, I add this power supply just to make it convenient for you to understand. Now I'm going to get rid of it because we don't really need that one to get the rest of it. Now I'm also going to remove this the original diagram. So if you want to have a look at it, you can obviously go back in the video and have a look at it. So I'm just going to get this one on its own so I can do the next step. Now, this one is actually pretty straightforward from this point onwards, because I can see the path from A to D to C, where you have two 10 ohm resistors that are in series with each other. Same thing at the bottom, two 10 ohm resistors that are in series. I can just add them up. Also, here I got in the middle, I got this 10 and this 10. These two are in series. So are these two. So I'm just going to add that to my diagram now. Now I can combine the two 10 ohm resistors at the top on the green path. 10 at 10, I have 20 here. The bottom one's 10 at 10, I have a 20 here. Then I got this 10 ohm resistor here. On the other side also there's a 10 ohm, but the middle two, 10, 10 becomes 20. The bottom one's also 10, 10 becomes 20. Now I can simplify this relatively easily. The two middle resistors are now connected in parallel. So the total of these two is 10 ohms, right? Because 1 over 20 plus 1 over 20 equals 1 over R total. Now that 10 ohm, this 10 ohm and this 10 ohms, they become 30 ohms. So I can simplify this now as just three resistors in parallel with each other, where the top one is 20 ohms, the bottom one is also 20 ohms, the middle one is 10 at 10 at 10, 30 ohms. So to get the final value for the total resistance of the cube network, all I need to do is 1 over 20 at 1 over 30 at 1 over 20. So R total is 7.5 ohms. Now that is the final answer. So when you have 12 10 ohm resistors connected in the shape of a cube, right? So we did the simplification. So we first flattened the figure, and then we found this balanced Wheatstone bridge so that we could remove certain resistors, and then it simplified to a normal number of resistors that are in series and parallel, and you just need to simplify them. So the final answer is 7.5 ohms.